Okay, so we just did our exploration, and we learned our new definition for eccentricity is FP over PD. So we're going to look at this picture. And there's a lot going on here, so let me explain what's happening in this picture. Here's F. F is the focus of our conic section. And we just saw from our last exploration that that's at the origin. Does everyone see how that's at 0, 0? Yep. Okay, here's point P on our conic. And our conic could be a hyperbola, it could be a parabola, it could be an ellipse, it could be a circle. It doesn't matter what it is right now. Point P is some point on the conic. And then on the other side of the conic, we have the directrix. That's this line D here. That's our directrix. So our first bullet point, what is the distance from F to P? And don't overthink it. It's actually already labeled for you. What's the distance from F to P? But it's R. What about the distance from capital P to capital D? Get your picture. Okay, so do you see the little p? The little p is just that distance there. So we also need this distance here. We don't know if it's p, so you can't say 2p, because this is not guaranteed to be p. But this piece, let me do it in blue so you can see it. This blue piece here is equal to this blue piece down there, because it's a rectangle, right? The opposite sides of a rectangle are congruent. I can figure out the length of this piece using trigonometry. Here's theta, and I know r is my hypotenuse. Is this blue side adjacent or opposite of theta? Adjacent. So what trig ratio uses the adjacent leg and the hypotenuse? Cosine. So I know that the cosine of theta equals, I'm going to call this x because I don't know what it is. X over what? R, because r is the hypotenuse. So then solving for x, what would I do to solve that for x? So I multiply both sides by r. So this length is r cosine theta. Opposite sides of a rectangle are congruent, so up here is also r cosine theta. So what is the distance from capital P to capital D? Good. The little p plus r cosine theta. Oh yeah, it does look like a polar equation, huh? All right, so now, that third bullet point, write the formula for eccentricity. We already did that, so let's move that over here. So eccentricity is Fp over Fd. And we just figured out Fp from our first bullet point. What's the distance from F to P? R over, and what's the distance from P to D? Good. So this is another way of writing the eccentricity. The eccentricity is also equal to R over P plus R cosine theta. We're going to rewrite that for the next bullet point. And we are going to solve the equation for R. So right now we're going to show off all of our algebra skills and solve this equation for R. So first things first, I have a denominator. So I'm going to multiply both sides of the equation by the denominator. And so on the right side, it cancels out. So I just have R equals. And then on the other side of the equal sign, I have to distribute that e. So I get EP plus ER cosine theta. I'm sorry? Oh yeah, the E is distributed. So remember, this was the definition for eccentricity, and then E gets distributed to both the P and the R cosine theta. Our goal is to solve for R. That's what we're being asked to do. So I want you to notice right now there's two R's in the equation. There's the R that the whole thing equals, and there's an R in this second term over here, ER cosine theta. So when you're solving for a variable, it can only appear once. So what we're going to do is we're going to put both R's on the same side of the equation so that everything that has an R is on the left and everything that doesn't have an R is on the right. So I'm going to move this term here to the left by subtracting. So the left side now reads R minus ER cosine theta equals EP. So that everything that has an R is on the left side of the equal sign, and everything that doesn't have an R is on the right side of the equal sign. Now there's a GCF here. What's the GCF in those two terms? It's not E. The first term doesn't have an E. It's R. So we're going to factor out the R. R divided by R is 1 minus, and when you factor the R out, you're left with just E cosine theta. And it still equals EP. And then there's just one more move to get R by itself. What's the last move going to be? Divide by, not by E, the entire thing, 1 minus E cosine theta. Do the same thing on the right. So our final equation is R equals EP over 1 minus E cosine theta. No, you can't factor out the E's because it doesn't appear in the first term there. It doesn't appear in every single term, so it can't be factored out. It's not a GCF. Exactly, yep, we have to get the R alone. So this right here, this equation is a polar equation because it's written as R equals, and the input variable is theta. And this equation represents all conics. It represents an ellipse, or a parabola, or a hyperbola. The only conic it does not represent is a circle. Because remember, we've already learned the equations for circles. Yeah, circles are just R equals A cosine theta or A sine theta. We've already done circles. So it represents all the other conics besides a circle. So we can use this now to graph ellipses, parabolas, and hyperbolas, and we're going to do that next. So I just want to show you that if we went to the next page, it's another derivation. We don't need to do this one. In this derivation, all we've done is we've put the directrix on the opposite side, so we are going to skip that.